All right, so had a quick lunch and I'm ready to go again after a cup of coffee. So where he left off was adiabatic quantum computing, and now he's going to talk about quantum annealing. Adiabatic essentially was when the transverse field interacted with itself, which equivalently you can perform any universal quantum computing using that. Didn't see the proof, but taking them at their word. And I guess over here they're going to talk about how D-Wave is able to focus on a subset of problems that they can solve.
Anneal over and over again. Say, anneal 1,000 times. It doesn't take long. It takes maybe 50 milliseconds. And then you can pull out these 1,000 different configurations and look at the energy levels and pick the one with the lowest energy. So this does not give you any guarantee that this is going to be the ground state and the global optimum for your problem, but this might give you a better solution than what, say, a classical heuristic algorithm would give you. And there's some work going on where you can bound how far you are from the actual solution by using some fast classical heuristics, and then you will get an idea whether you are in the ground state or whether you're actually close to it.
Right.
So in principle, this model works very well. And then if you want to perform universal calculations, you must have both sigma z interactions, like between the sigma z operators, and also between sigma x operators. This is, again, something difficult to achieve. So if you resort to just solving the classical Ising model, then you can solve these quadratic unconstrained binary optimization problems, QUBOs, which are NP-hard, so there's value in solving specific operations as opposed to solving a much harder problem that allows you to perform universal calculations. Then there are all sorts of experimental conditions that you face. For instance, there is a 2,000 qubit quantum annealer implemented by D-Wave Systems. This is a superconducting architecture, which means that you have to cool it down to about 10 millikelvin or so. But that's not absolute zero. So you're operating at finite temperature, which means that, in principle, you even don't, it might happen that you don't even get the ground state to begin with. And there's a higher chance of jumping out of it as you perform the transition. And then there is this problem that the electronic control that goes into the actual quantum chip interferes with the calculations.
Right.
So the machine itself sits in a big box, which is a Faraday cage. It shields the device from external electromagnetic radiation, but the classical electronic circuit itself introduces some noise in the system. So these are intrinsic engineering challenges which will interfere with your actual calculations.
Right.
Yet, this is a very interesting model, and you can get very interesting calculations by performing repeated annealing round. So we talked about the software stack for gate model quantum computers. So let's take a look at how it works for quantum annealing. So we can start again with the problem definition. For instance, we can address the same problem, the traveling salesman problem. We have to visit n cities and choosing the shortest possible way of visiting all of them. Then it easily maps to an optimization, a quadratic binary optimization problem. So that's intrinsically an Ising model. So this is easy to do. And then what we have to do is something called a minor embedding. So this step corresponds to the compilation in the gate model architecture. So in compilation, several things are going on. First of all, you map from some gate sets that you define in a circuit to the actual hardware, and then you also factor in the constraints of your architecture. For instance, if two qubits are not connected and you want to interact with the two, then the compiler has to do something to allow for that interaction. And when it comes to minor embedding in an annealer, what can happen is that your qubits may not be fully connected. For instance, in this 2,000 qubit architecture, you have these unit cells consisting of 8 qubits,
Right.
and 4 qubits are fully connected between these two sides.
Right.
And then each one of these qubits have longer range interactions to the next unit cell,
Right.
which is the same thing as writing this graph and having these long range connections
Mhm.
to the neighboring unit cells. So your problem has some intrinsic connectivity structure, and then this minor embedding, this graph minor embedding, is what embeds it in what the hardware actually provides. And then you can map it to the QPU and run your annealing over and over again in just a couple of milliseconds.
Mhm.
So to be more specific, imagine that you have this problem. So you want to find the minimum energy configuration of sigma 1 times sigma 2 plus sigma 2 times sigma 3 plus sigma 1 times sigma 3. If you write down what's the connectivity structure of this, it's actually a K3. So here you would have sigma 1 interacting with sigma 2, then you have sigma 2 interacting with sigma 3,
Mhm.
and finally you have sigma 1 interacting with sigma 3.
Right.
Now if you look at this graph, there is no K3. This is a complete graph on 3 nodes. So what you do is, for instance, this would correspond to your logical variable sigma 1. That's fine. This
Right.
corresponds to sigma 2. That's also
Right.
fine because they interact, so they are connected to each other.
Right.
And now you can create another logical variable by combining these two physical qubits.
Mhm.
So these two would act as a one logical qubit, sigma 3, and you increase the coupling here to make sure that these two physical qubits always have the same value to
Mhm.
represent the same logical qubit. So you introduce a strong coupling here as a way to mimic the connectivity structure that you are looking for.
Right.
So this task in itself is hard, so you use probabilistic methods to embed the problem that you have on the hardware. But once you do that, quantum annealing is an interesting and a straightforward thing to do on your optimization problem.
Mhm.
We talked about
Let's keep going. So implementations, superconducting architectures, silicon-based, cool around 10 millikelvin microwave pulses control the system. Disadvantages is two-dimensional topology, right? Cooling requirements, short coherence times, yeah, limited circuit depth. Versus trapped ions, individual ions, charged atomic particles, confined using electromagnetic fields, laser-induced coupling. Long coherence times, the disadvantages are scalability is unclear, and speed of control, well, neutral atoms have scaled pretty well, seems. Photonic systems, example, photon polarization, room temperature. Disadvantages, photon loss, photons cannot be stored. Yeah, okay.
an abstract description of gate model quantum computers. We talked about quantum annealers, but we never talked about how you actually build one of these things. So let's take a look at the couple of competing approaches today which could scale up to larger quantum computers. Well, the most popular approach is superconducting architectures.
Mm-hmm.
So in this case, you are using a silicon-based technology. This is great because you can use the same fabrication facilities as you would use for building your digital circuits in your phone or in your laptop. The only difference is that you cool it down to around 10 millikelvin with a massive refrigerator. And then you use microwave pulses to induce control and actually implement the gates and the interaction between the different qubits. And microwave pulses are great because control speed is very fast. You are in the range of nanoseconds. So in principle, the speed of this system is very, very good, but there are a couple of problems. First of all, since you have this silicon wafer, this is fundamentally two-dimensional. So imagine now that you have 4 qubits implemented, then you can have full connectivity between every pair of qubits. So you can apply gates between any pair of qubits. But the moment you add a 5th one, that goes away, because there's no way to connect this 5th one with all of the other ones. You cannot cross the wires. So when it comes to a problem like this is where the quantum compiler starts to play an important role. Because what it would do if you want to interact these two qubits, it would implement something called a swap. For instance, it would swap
Create a default swap?
these two, perform the interaction, and then swap them back. That's the easiest thing to do. And the swap is very simple. So if you look at the circuit diagram of it, this is just a control node, followed by a control node the other way, and then a third one. So it introduces 3 gates to swap it here. And then you perform the gate that you wanted, and you could swap it back. So you would look at 7 gates just to perform 1 gate operation. This will be a problem. So the problem is short coherence time. So in these systems, you look at very, very short coherence times, which means that you can only execute gate sequences which are very short. So your circuit depth is basically the number of gates that you have lined up on your circuit. And this depth is very limited. And how limited it is? Well, we are looking at 10 to 20 gates. And now you're using up 3 gates just to swap these two. So that's a fundamental limitation in this architecture, and you have to be very careful when you design algorithms and compilers, because you want to avoid introducing extra gates in your compilation. Plus, these systems have cooling requirements. One of these refrigerators costs $500,000 on its own, so that's a major engineering bottleneck. Then we have trapped ions. In this case, we take individual ions, which are just charged atomic particles, we line them up, and we trap them in an electromagnetic field, and we use laser pulses to control their interaction.
Right.
These are fantastic. They have a long coherence time, but they have their own disadvantages. Scalability is unclear. So recently, there are systems up to above 70 qubits implementing this system.
It's more now because this was 5 years ago, so.
But it's unclear how well it will scale to larger and larger systems, because we ideally want thousands of qubits. And the speed of control is much slower than in the case of superconducting architectures. Then we have photonic systems, for instance, which are just light. You can take, for instance, the polarization of the light as qubit states.
So it would have been nice if you spoke more about why the speed of control was slower. Anyway.
It would be left polarized, right polarized, and a superposition in between. And they operate at room temperature, so that's fantastic. But the problem is that these photonic circuits have photon loss. You can characterize it, but this loss is going to be there. And then photons cannot be stored, unlike these ions, which are suspended, or the silicon-based architectures, where the actual artificial atom or the flux qubit is actually carved on the silicon wafer. These are elusive in nature. So it's unclear which one of these architectures is going to give us a large-scale perfect quantum computer. And there are also a couple of other approaches to try building one. So at this point, we just have to wait and see which one proves best.
Nice.
Most men over 40.
Quantum approximate optimization algorithm, yep.
We talked about gate.
Variational circuits, system, quantum processing unit, environment. There's a new breed of quantum algorithms since 2013, parameterized shallow circuits, approximating the adiabatic pathway, right ground state, right state space. Okay.
Gate model quantum computers. We talked about quantum annealers, and we also talked about how we implement them. And we saw when it comes to implementations, we introduce imperfections. These imperfections prevent us from running the most famous quantum algorithms on these quantum computers. And there has been a change over the last, I would say, 5-6 years in mentality. So we started to develop a new breed of quantum algorithms, which are called variational circuits. So these are designed for noisy and imperfect quantum computers. Because if we have a system, which is our quantum processing unit, it's embedded in an environment, whether it's a superconducting architecture, whether these are trapped ions, there's always an environment. And there is some interaction going on. So you will face decoherence and equilibration, all sorts of strange processing going on. So we have this limited ability to control the system, and this limits circuit depth, for instance. So what we want to do is run a short burst of calculation on the quantum processing unit, extract the results to a classical CPU, and then the circuit that we ran on the quantum computer is parametrized. So by understanding the results of a calculation, we can go back, adjust the parameters of the quantum processor, and again run a short burst of calculation, and it becomes this iterative loop. So one of the most famous variational circuits is quantum approximate optimization, or QAOA for short, which actually draws inspiration from quantum annealing. So what we are trying to do is approximate the adiabatic pathway, but on a gate model quantum computer. So remember that what we do here is we calculate the ground state of some simple Hamiltonian, say just the sigma x interaction on every single site. The ground state of this is just going to be the equal superposition of all states. And then we follow this adiabatic pathway, and if we do the transition slow enough, then we can read out the ground state of the system that we are interested in, for instance, the Ising model.
Right.
So the gate model quantum computer, what we do is we break this pathway up into discrete chunks.
Mm-hmm.
And the way we parameterize the circuit is to have a more and more accurate approximation of this transition. So at the end of it, you would actually read out the ground state just the same way as you would do it on a quantum annealer. So we have this transition and that we want to approximate, so this time-evolving Hamiltonian.
Mm-hmm.
And say up to some time t0, we could approximate it in two steps. So one, say, going this way, and the other going this way. First, we would apply the first Hamiltonian, the sigma x interaction, for some duration beta 0, followed by the application of the second Hamiltonian for some duration gamma 0. And then we can have subsequent time steps. And we multiply them together. So this approximation is known as trotterization.
Trotter.
And you can control the accuracy by increasing the p. So the more steps you have in the discretization, the more accurate your optimization is going to be. So this way, now you can...
Well, it seems a little bit counterintuitive because your initial desire would be to make it in as few steps as possible with as few classical perturbations, or I guess without filtering through the classical CPU. But I guess the math shows otherwise, so that was a bit counterintuitive.
Formulate an optimization problem over these parameters and do say a gradient descent to actually find the ground state of your target system.
Probably takes a lot of resources and time.
Say good.
Yeah.
We talked about variational circuits, which are quantum algorithms designed for imperfect quantum computers.
Right.
We can also take it one level further and just accept imperfection and accept that when you have a system, say a quantum annealer, then it interacts with the environment. And if you let this equilibration happen, then we know that the end of it, we are going to end up in the thermal state. So the thermal state is in this thermal equilibrium with the environment. So the environment has a temperature, and the system attains the same temperature. And if we pull out samples from this thermal state, and they follow a specific distribution. They follow a Boltzmann distribution. So this is critical because every time when you face the problem of pulling out samples of a Boltzmann distribution in machine learning, you can just plug in this idea of annealing to sample the thermal state. The only difficulty is that this temperature is not what you read out in the thermometer in your dilation refrigerator that cools down your superconducting system. It's an effective temperature which comes also from the noise and other factors that surround the quantum processing unit. So this has to be estimated, but once you do that, you can use this as an algorithmic primitive. You're not restricted to a quantum annealer. You can actually do something very similar by using a gate model quantum computer. So this is called quantum approximate thermalization. And to get the idea, just go back to the first module. In one of the videos, we talked about that if we take the maximally entangled state and we marginalize over one of the subsystems, it doesn't matter which subsystem. In other words, we take the partial trace in one of the subsystems, then we end up with the maximally mixed state. Now, the maximally mixed state is just the thermal state at infinite temperature. So I can think, can we take this idea further and have some larger system, trace it out, and get the thermal state? And that's exactly what you are doing. So you create some easy system, for instance, the sigma x Hamiltonian acting on each site. And you take an NC-love in the same number of qubits as the number of qubits you have here. And if you start, for instance, with just 1 qubit for the sigma x interaction and 1 qubit for the ancilla, then you can take this state, which looks remarkably like the maximally entangled state. So now you have the plus state. The plus state is just the equal superposition of 0 and 1. And the minus state is the same thing with the minus sign here, so we can just write it this way. So it looks almost identical to the maximally entangled state, with the exact difference that you have these coefficients in front of the individual terms and some normalization factor. Now, this is the ancilla system, and this is your actual system that you're interested in. Now, if you trace out the ancilla system, what you're getting is exactly the thermal state of this Hamiltonian. So this was easy to prepare. And it's just the same idea as we did here. And now we can use, as a second step, the quantum approximate optimization algorithm to go from here, from this rho 0 thermal state, which is in equilibrium with the environment, to the thermal state of a system of interest, for instance, the Ising model. And the QAOA approximates a unitary evolution. In other words, it's not going to change the thermal equilibrium. So you will always stay close to the thermal equilibrium. So once you finish optimizing over this parametric circuit, you will be able to read out an approximate thermal state of the system of interest.
We identify your risk of stroke.
You will be able to read out. See, that's where people start to get lost, because it would be nice to give a more intuitive physical example. But, I mean, that was almost like a side note that you can also do it on universal quantum computers. They don't really care that much, so I'm guessing they're going to go back to annealing. So variational circuits and quantum simulations. So, right.
Hello. Today we're going to talk about variational circuits and quantum simulation. This is one of my favorite topics because I've been heavily involved in it for the last decade and a half, I guess. So let's just begin where it all begins, and it begins with the famous Richard Feynman, who in 1982, in a seminal paper in the International Journal of Theoretical Physics, proposed that quantum devices, that in this case I will call quantum simulators, could simulate natural physical phenomena efficiently. Okay, so this lecture is about that, and then how we enter into the topic of variation in circuits. So why was that seminal paper so important, to the point that it cited more times than the work of Feynman for QED that gave him his Nobel Prize? The reason is because that's the foundation of our field, right? That was one of the first papers where the idea that computing or using a quantum system for simulating another quantum system was going to give us some definite advantage. And Feynman was a very intuitive researcher, a very intuitive scientist, and very charismatic. So what did he have in mind can be explained very simply in the equations that I have here on this side. This psi is the wave function of a system that I want to simulate. Okay? Think about it as a condensed matter system, or a molecule, or some other place where quantum mechanics plays a role. And then imagine that I have some mapping, and the art of quantum simulation is finding that mapping, that takes such a wave function to the wave function of a controllable quantum system that I will be calling quantum simulator. Here are the indexes, S for the system, and QS for the quantum simulator. The time evolution of the quantum system is determined by the unitary time evolution operator, which is this imaginary exponential of the Hamiltonian times time, right? So you have this natural system that is evolving with this Hamiltonian evolution using this unitary time evolution operator that is mapped to this controllable Hamiltonian that might be different, but it's meant to basically mimic the same dynamics on this quantum system. So Feynman's key insight is that any observable obtained on this side of the equations will be equivalent to any observable obtained on this side of the equations, right? Because after all, these kets for these quantum states will be indistinguishable from each other, and the evolution as well will be to some tolerance indistinguishable, right? So in some sense, he had the intuition that if you want to simulate the dynamics of a quantum system, why not exploit the natural quantum dynamical evolution? Okay? Okay, so I actually found my first typo. Okay, and I hope the one that found it gets many brownie points. We're talking about then, 14 years later, an inspiration for me, a colleague, a mentor, and a friend, Seth Lloyd, professor of mechanical engineering at MIT. He calls himself a professor of quantum mechanical engineering, made another key seminal contribution. So what Seth did is formalize and completely make the basis for Feynman's idea. In other words, he grounded it. And he proved that quantum simulation for what I like to call natural Hamiltonians is efficient. In other words, a quantum simulator or a full-blown quantum computer can do it. So now we're going to go into the mode of a full-blown quantum computer and thinking of the gate model of quantum computation. Okay? So, first terminology, I'm introducing here this term k-local. K-local means that an operator is acting at most k qubits. Okay? So, a k-local Hamiltonian is a Hamiltonian that acts on at least k number of different qubits. That in simulation we usually have some mappings that a qubit or a group of qubits or some mapping to the qubits will represent some site on a system. In condensed matter physics, it could be a site where electrons are hopping around. In chemistry, it could be an orbital, etc. So some unit of the quantum system that you want to simulate. Okay? So just terminology, right? This is the system Hamiltonian that we already discussed here that can be partitioned in different terms. And just remember that Hamiltonians really are just energy functions. Okay? So this is just counting all the different contributions to the energy of the quantum system that in turn determine its dynamics. Okay? And again, all these terms have this rule that they can only act on at least a certain number of qubits given locality. Okay? Very important feature for being able to do simulation. Okay? So the important result from Seth Lloyd is that these Hamiltonians, okay, can be implemented efficiently, and it is because the number of terms, L, okay, scales polynomially on the system size n. And usually it's a low polynomial, order 4, for example, for the applications that I really like.
With Asana, tasks, and company.
Kick off the new year with a
So, does this matter? Does quantum simulation really matter?
Variational circuits and quantum simulation. So,
I think it matters because the name of my own lab is the Matter Lab. And why I named my lab the Matter Lab is because since 2005, when I started introducing this quantum simulation to the field of chemistry, right, we started thinking about the importance of exactly simulating molecules and materials. You could design new catalysts, potentially find new drugs, potentially find stronger substances that could actually help the planet achieve, for example, climate emission goals. So it's a novel idea to think about if quantum computers could actually simulate molecules. So why don't we basically spend a little bit of time thinking about the specific case of molecules, because that will inspire us later into thinking about variational algorithms in general. So what we identified is the idea that you can think about qubits, okay, the same way as Seth Lloyd was saying, as natural representations for orbitals, okay, with a caveat that I will mention. But basically, you can imagine that an orbital in this particular case can be occupied by two electrons, a spin up and spin down electron. And this is a hydrogen molecule. It will have a bonding and an anti-bonding orbital. There are combinations of these local orbitals localized in the hydrogen atoms at the center of these cusps here, right? So this is an H2 molecule, and its minimal representation will be these two orbitals, right? So you can imagine using two qubits to represent each one of these orbitals, because one of them will represent the presence or absence, or a spin up or spin down electron, okay? And then another two qubits to represent this particular orbital, is there or not a spin up or spin down electron, okay? So that's just a very simple mapping, okay? But of course, as I like to say in all my lectures and all my online lectures, Hamiltonians are counting energy contributions, okay? They are just energy cost functions, right? So the Hamiltonian or energy function of a molecule, again, sums over L terms. There's actually n to the 4 air terms, basically because of this index term here, and n squared terms here, okay? That sum over different orbitals. But notice these operators that Peter tells me you have not seen so far in this course, okay? And these are called fermionic destruction and creation operators. So they eliminate an electron from an orbital and add it to another orbital. In other words, I could apply a destruction operator to eliminate this spin and actually create it here in this particular orbital. So it shuffles the electrons around, okay, spin up or spin down electrons into the different spin orbitals. So what is the energy? So first of all, this two local term, okay, because it involves two fermions. So it's two local in the fermionic sense, okay, is related to what we like to call in chemistry the two electron integrals. Which are parameters that come from a computer, a classical computer computes these parameters, and tell you what is the amplitude of hopping from one orbital to the other due to the kinetic energy of the electron and the electron nuclear attraction. So these are terms that only depend on a single electron that can go from one side to the other. And there is a competition of the attraction to that particular side, the nucleus here, and the kinetic energy T that makes it hop between them. Right? So that is a two electron term, and it's two local because it involves these two fermionic orbitals. And a more complex term that we will, as chemists and condensed matter physicists, we like to think about, is the electron-electron repulsion. This is a many-body term because if there's an electron fluctuating somewhere, it's going to influence another electron. Okay? So the way you want to think about it is the presence of two electrons. So these amplitudes represent if two electrons are in two orbitals, what's the probability that they will jump together to two other orbitals, right? And all those possible combinations, right? To all those different types of orbitals. And there's a lot of terms, there's n to the 4 of those terms, and they all depend on the electron-electron repulsion. And again, these parameters, these two electron integrals, and these so-called 4 electron, excuse me.
I have to say the other two were better. This is he's not doing a very good job of explaining this, I have to say.
Again, you guys found my first typo. This is a 1 electron integral, and this is a 2 electron integral. Okay. Again, because this is representing the dynamics of a single electron hopping around, and this is the dynamics of 2 electrons hopping with each other. So if you got my typo, you got a brownie. Okay? So, and these 4 electron integrals, of course, are 4 local in the fermionic sense.
I mean, I'm following what he's saying, but my brain is also finding it much harder to follow him because his teaching style is not that good.
Excellent. So, what is really cool about this is that once we have this Hamiltonian, I told you already that Seth Lloyd had built this fantastic machinery to simulate this guy by using a technology called trotterization that Peter already told you when he was talking about the QAOA algorithm, right? Which is a hybrid quantum classical algorithm, very related to what we're talking about, right? So it is in that sense that we can numerically exact simulate matter. Okay? So what do we mean by numerically exact? We pick a basis of orbitals that is finite. If you think of atoms, that's basically the angular momentum contributions of each particular atom. That's how that are combined into these molecular contributions. Okay? So within that particular precision that is given by that particular finite basis, we'll map it to qubits, and then we will use these qubits to build, we'll map it to Hamiltonian that will be mapping in turn to qubits. There is a technical detail of how to go from fermions to distinguishable spin 1/2 particles, which are the qubits. Okay? So these are fermions, undistinguishable particles. Guess what, guys? Qubits are distinguishable. If I look at a qubit, I know a qubit is here or a qubit is here. Okay? So this is qubit A and qubit B, whereas electrons in principle have to be undistinguishable. So this is a mathematical operation called Jordan-Wigner transformation that is implemented in terms of quantum gates that allows you to map the algebra of fermions to the algebra of qubits. That's a technical detail that you can learn more about in the technical component of this lecture, and also in this monumental, gigantic review paper that we wrote about the topic. And I'm trying to give you here the review paper and the pages associated. Deal with it. Okay. So what is the cost of this? Big cost of this?
I mean, he should have broken it up and he should have added. It would have been nice to get some intuition about that process, as opposed to just saying, oh yeah, look, we made this monumental paper, it's huge, we're so smart. Yeah, it's more messy, so it's more messy and clumsy.
This Jordan-Wigner transformation and the Trotter approximation and so on, the cost is empirically about n to the 6. Okay, so n is the size of the system. The way you're going to think about the size of the system, not to complicate things, imagine a bunch of water molecules that are very practically not interacting with each other. So you have water molecule 1, water molecule 2, 3, 4, 5, 6. And when I say the system grows, instead of having, for example, 6 water molecules, you have 12 or 18 or 20. So that will be n. Okay, that's a way of thinking about what I mean by the chemical system. Or think about a molecule that keeps growing with more and more atoms. The way you want to think about it, just add more and more atoms, proportional to n. So that cost is quite dramatic. Okay, so our initial estimates require hundreds of thousands to millions of gates, and that in turn requires error-corrected quantum computers. Having said that, an extremely diverse number of researchers, since our very early work, have lowered down the cost and introduced more and more complex algorithms. And here, I really want to emphasize many researchers, but especially my former student Ryan Babouche, now at Google, has really, really made an impact with him and his collaborators in having lower cost algorithms, right? That actually lower this, basically to this linear scaling type on the system. Of course, there's polylogarithmic factors and things like that, and scaling on the errors that you can read on his papers and also on our review paper. So this is kind of like the general picture of why you want to simulate a molecule. I will just end saying, again, that simulated molecules can unlock very interesting applications of commercial interest, which is important for the justification of all the investment that all the nations are putting on quantum computers.
Oh man, it went downhill really fast. I'm not looking forward to this. So I really don't. I don't like this style. Instead of giving physical intuition behind some of the key elements and walking you through it, it kind of just feels like a mess. It's very messy.
So in my research group, we were quite concerned about the cost of quantum algorithms in the fully error-corrected way to simulate molecules. We know those algorithms that I described previously are going to be asymptotically the best algorithms to do chemistry. But what can you do with a quantum computer that you have in present? At the moment, we just call them near-term quantum computers. Recently, our colleague John Preskill from Caltech started calling them NISQ, near-term intermediate scale quantum computers. And we are now in the so-called NISQ era. So contemporaneously to the QAOA algorithm of my friend also and mentor, a fantastic friend, Eddie Farhi, which is, his claim to fame is that he has pulled weights now that he lives in LA next to Arnold Schwarzenegger. Okay, so that's Eddie. Eddie developed QAOA at the same time, roughly, that we were developing the variational quantum eigensolver. As a matter of fact, we spoke back to back at a conference, and we both were like, our algorithms are quite similar. And those two algorithms were the first hybrid quantum classical algorithms. Okay? So what exactly is a hybrid quantum classical algorithm? It's an algorithm that uses the quantum computer like a lime in a Mexican restaurant. You exploit all the power of the lime for preparing a quantum state, okay? And you trade off a lot of the complexity of the algorithm by a bunch of measurements, okay? So in other words, what you're going to be doing is you're going to calculate, you're going to be preparing quantum states, and then you're going to be measuring them, and preparing and measuring them. So you might say, okay, so what's the point? Well, the point is that you can actually take a lot of operations that are very hard to do on a quantum computer and dump them into a classical computer, such as optimization and such as addition, division, etc. So these arithmetic operations require a lot of gates that now you can actually offload to the classical computer that is controlling the quantum computer as if it was, say, an accelerator or an auxiliary system, if you think about it as a GPU or something like that. Okay? So the way it works is the following. First, you're going to define a quantum circuit that I like to call it a stencil. This is a quantum circuit that has a certain shape, and each one of these elements here, 1 or 2 qubit gates or multi-qubit gates, we have one or more parameters. Let's say each one of them has one parameter. Usually they have more than one, right? And these parameters, I like to call them little lambdas, right? Are little parameters that together form a parameter vector. And what did I use? I use m, okay, for the number of parameters. So I have m parameters, okay, that at the beginning I might set up with a classical guess. I might set them up randomly, and I prepare a quantum state, and I measure. And in my case, I'm simulating molecules, so what do I measure? I've been talking about it in the last lectures. I measure the energy of the molecule, and therefore I measure the Hamiltonian. Okay, so what I do is I take a molecule, measure the Hamiltonian, okay, and then go to a classical computer, okay, and then figure out what is the energy of that Hamiltonian, and then I use the variational principle, which I will describe in the next slide in more detail, to actually change the parameters of the in such a way that the energy of the Hamiltonian is lowered. Okay? Again, we'll go into the mathematical details of the variational principle, but at the moment I wanted to give you the big picture of how all these hybrid quantum classical algorithms work. You prepare a quantum state, that's the first phase. Okay? Then you measure.
Mm-hmm.
And then you're going to update the parameters.
Right.
This big lambda is the parameter vector lambda that determines all the parameters of the wave function. And once you update the parameters, you fit them back in, right? So if you started with, say, lambda 0, the first iteration, this guy is going to go around and give you lambda 1, which is going to be a better iteration. And then after that, lambda 2 and lambda 3 and lambda 4. And you continue optimizing.
Right.
Not dissimilar, of course, to the way neural networks are trained and other machine learning tasks.
Right.
So not surprisingly, this family of hybrid quantum classical algorithms look a lot like the original variational quantum eigensolver and include people that have done quantum classifiers and so on. And because I don't want to offend anybody, I want to tell you some of the algorithms we have developed. Of course, there's tons of other algorithms, but so some of the ones that we have done, for example, is one for error correction, the quantum variational error corrector, and two machine learning quantum algorithms, the variational quantum autoencoder and the variational quantum generator, okay, that we actually took out and posted in the archive in 2016 and 2019. And to these ones, I give the credit to my student, Jonathan Romero, and also together with Johnny Olson. But Jonathan Romero has been involved in these two algorithms, okay? So this is kind of part of his PhD, and we're very excited about them because they are machine learning algorithms that you might want to learn more about. They're exactly in the same family of algorithms, okay? So what is key about this is the fact that this classical computer needs classical optimization algorithms. A frontier of this field is how do we know that as m grows, where m, as you know, is the number of parameters, the classical algorithm is going to actually find the best parameters for the quantum circuit. It's a very interesting paper by Jarrod McLean at Google. Another one of my former students, I love to say that, but he's amazing, this guy. Okay, with Ryan and others, Ryan Babush, has explored this problem of what happens when this m grows, and then can we really still prepare quantum states? And they argue that perhaps you really need to have a good classical guess to be able to do this for large m. So there's many open questions in these hybrid quantum classical algorithms that I think are very current and are a key part of the course that Peter put together, because these are key questions for the usability of near-term quantum computers. So in the next slide, I'm going to move on and tell you how we use in particular the variational principle to do this in a
Right. It's starting to get a bit more interesting. It was very straightforward, so that was.
So finally, I want to talk to you a bit about the variational principle. So the variational principle is formally stated here. It says that, say you take a trial wave function. And what I mean by a trial wave function is a wave function that was prepared with that stencil for a quantum circuit. In other words, a circuit that has m number of parameters, this lambda, lambda 1, lambda 2, lambda 2, lambda 3, all the way to lambda m parameters that are, defining the family of quantum states that particular circuit stencil can reach. And a lot of the research I'm doing nowadays, I'm going to put a paper in the archive very soon, is how powerful are different stencils to generate entanglement, to generate the particular measures that we need for having variational freedom here. Because of course, the more free the state is to represent quantum states, the better you will be to lower the energy, because there's a theorem, the variational principle says, this variational principle says, that the better your wave function, the lower its energy, okay, the closer to the ground state energy. So this is a particular algorithm to go all the way down to the lowest eigenstate, okay? And there's generalizations to any eigenstate with different techniques, but let's just talk about the ground state. So if I had an infinitely flexible wave function stencil that covered all Hilbert space, I am guaranteed to get the ground state. But remember, we have a NISQ quantum computer that has a finite number of gates and a finite number of entanglers. And as the beautiful lecture of Peter told you, not only that, you have locality in your hardware. So, if you want to entangle two things far away, you have to waste perhaps a bunch of swaps to get there, right? So this is my, my compressed notation. This is a wave function that depends on lambda. This is a Hamiltonian, okay? Just to show you like the typical thing that you would see in a textbook, compressed version of this, with no denominator for normalization. But the point here is I just split it into all the different terms, okay? Because basically, the variational eigensolver, what it is realizing this, that you can prepare the wave function as a function of lambda once, measure the first term of the Hamiltonian, and then, of course, you projected your function. You have to start again. You prepare it again and measure this guy again. Prepare it again, measure the first one again for enough times, perhaps a few thousand, to lower the error of that particular term. Then you prepare the wave function again and do the second term. Prepare the wave function again and do the third term, several times each, because you want to propagate the error of adding and adding all these different terms statistically to come up with expectation value of the energy for that particular quantum state. Okay? So that will tell you just the first value of lambda. We call it lambda 0, right? Then you're going to have to do an iteration with your classical optimizer to vary lambda, right? The subsequent values of lambda to lower the energy. So typical variational eigensolver or variational
See, over here, I feel like I'm having to fill in the steps myself. So going back to when he was describing two electron system, you have a Hamiltonian. Now he's saying there's a wave function, but I'm kind of not tethered to what this wave function is. Like, what's the intuition behind your first wave function, right? And now you're trying to evolve, but I've completely lost the tether of what am I evolving from and to. Whereas before he started, I did get a sense that you were in a regime where you were going to quench. So you're going from T0 to TA or something for the annealer. And over here, I'm sort of getting an abstract understanding. And I guess that's good enough for now. So maybe down the line, they're going to put their intuition back into what's going on.
Algorithms or hybrid quantum classical algorithms require a lot of preparations and a lot of measurements. First of all, to lower the error here, and also to iterate over the classical optimizer and try to find a lambda that is optimal. And you don't know if you ended up in a barren plateau where you didn't go to the ground state at all, or you were in a local minimum. So you sometimes have to restart and do this again. Okay? So this is the cycle. You prepare a state.
And again, all of this is for the noisy quantum computers. So once you actually have clean quantum algorithms, a lot of this will either be redundant, so essentially it will just be legacy, or I guess they like to call it deprecated, or it can be reused for very long time calculations.
Measure each one of the terms, obtain the expectation value, rinse and repeat. Okay, this is what I was mentioning verbally. Here is just a laundry list of what you can do. And what is very nice is that you can write your own IPython notebook and actually do this, right? It's very satisfying when one of the leading ideas in quantum computing.
So this was 5 years ago, and 5 years ago, I guess they were excited that this was one of the leading ideas, but I haven't heard about too much about like any big results coming from this. So
It's easily realizable if you have a little bit of creativity. So this is one of the cool things about this course, that you actually get hands-on fun experience. Okay? So what is really, really cool about all of this is obviously that you can experimentally realize it. So in the case of molecules, Peter O'Malley from Google and collaborators, we were able to actually simulate, the lowest possible scalable hydrogen molecule, okay, both with the variational eigensolver and another technology called the phase estimation algorithm. Okay, so you can read that paper; it's really cool. And then in ion traps, Cornelius Hempel did slightly larger molecules like the helium hydride. And I guess I had an error in each slide, guys. So this Kandala paper from IBM is a Nature paper. It's actually a superconducting qubit experiment with 7 qubits. It's the state of the art now of a variational simulation of a molecule on a quantum computer. What is really cool is that I believe this year and the next year there's going to be many more experiments in perhaps a larger and larger number of qubits. If you want to learn more, there is this review paper, there is our group website, there is this course, and there's many other resources online that will teach you more about variational quantum algorithms.
Okay, if there's one AI site builder you
Irrespective of the choice of a quantum computing paradigm, you will always face the problem. How do I encode the classical information I have into a quantum system to perform some quantum protocol? So there are a couple of ways of doing it, and here's an overview of all of them. The easiest thing to do is to do something called basis encoding. So in this case, you don't do anything different from what you do on a digital computer. So say you have the number 3 that you would like to encode, then you would write it as a binary. So this will be the representation of digital computing, where this is bit 0 and this is bit 1. And then you just take this and you write it as a quantum state. So you would use 2 qubits, and you would flip both of them to 1, and it would describe the number 3. And if you have a vector, say, of these 2 elements, you can create a binary vector of that, and then you can concatenate the 2 strings into a single cat, into a 4-qubit state in this case. So the greatest advantage of this encoding is that it's very easy to prepare, because you only have to flip certain qubits. Most quantum computers start from being initialized in the 0 state, and then you just have to make these NOT operations, the X operations, to get to the state that you want to express. But the great disadvantage is that it's very wasteful of your qubits. You need lots of qubits to describe, say, floating point numbers. Another way of doing it is amplitude encoding. So imagine that you have a vector, and let's have this assumption that your vector is already normalized. Its length is 1. Then what you can do is just write down the same thing with the original coefficients, indexing the individual coefficients or probability amplitudes with the basis vector. So the advantage of this is that it requires a lot fewer qubits. And in principle, at least in theory, This is of infinite precision, so if you have a real number here, you would have a real number here. But the disadvantage is that it's unclear exactly how you would prepare this state and how you would read out the actual values here. So you would have to dream up some state preparation protocol, and then you would have to perform tomography to understand what these probability amplitudes are at the end of your calculation. Then we can also encode the problem in a Hamiltonian. So when you think about it, there are actually two ways of doing this. One is that we have seen over and over again. This is the Ising way. You have a problem, you map it to the Ising model, or a quadratic unconstrained binary optimization problem, which is given in this form, and that's what you saw, for instance, by quantum annealing. So the encoding comes in these couplings and these bias terms. These are the ones expressing your problem. Whereas here it was the state, and here it were the probability amplitudes. So the advantage of this is that it's fairly easy to implement. We are up to thousands of qubits in a physical system implementing this model. But the disadvantage is that it has a very limited scope in what you can do. You can solve either optimization or sampling problems with this paradigm. Then the second way of doing Hamiltonian encoding is by doing Hamiltonian simulation. Now, this simulation is a bit misleading because this is not a simulation on a classical digital computer. This is a quantum computer simulating a quantum system. So what you are doing is actually you are trying to implement this unitary on a quantum computer. And an example of this is exactly what the QAOA optimization algorithm does when it approximates the adiabatic pathway. And a very, very important subroutine in many idealized quantum machine learning algorithms is quantum matrix inversion, and it does the exact same thing. It encodes the matrix to be encoded here in the Hamiltonian. So the advantage of this is exactly this. It's very natural to encode the matrix in this formalism. The disadvantage is that there are countless terms and conditions that apply. So we'll only see quantum matrix inversion in the part where we talk about coherent quantum protocols and large-scale quantum computers. And it's very, very limited what we can do on actual quantum computers today when we want to use this representation.
All right, let's go. Come on.
So we talked about quantum computers. We talked about how to encode classical information in quantum computers. And we are getting ready to start talking about how you do learning on the encoded information in a quantum computer. But first, let's talk about a couple of things in machine learning. So when we talk about optimization in machine learning, we typically don't talk about the kind of optimization that you would perform on a quantum computer. So in a typical scenario, you're given a sample. So you're given a couple of data points in some high-dimensional space, each coming with some label. The labels can be 0 or 1, or belonging to some finite many classes. So what you're actually learning in the machine learning model that you're trying to fit to the data is a conditional probability distribution. So
Okay, so ensemble learning, optimization in machine learning. X is, can't read that. S is a subset, no, S is xi, okay. Coordinates, perhaps. Real numbers between 0 and 1. Discriminative D supervised. Min theta L. Okay, function, minimize, okay. Q belongs to real numbers to P. Can't read that. Deep learning. Alright. So you have ensembles. It's an ensemble. H1 to HK. So f of k is equal to the sum of of HK. So I guess that's sort of like a energy. ADA boost, sequential expansion of the ensemble. So you sequentially expand it. Fm is equal to Fm minus 1 plus the remaining term. Wm is derived from the exponential loss. Sum of e to the Okay, I'm lost here. Regularization is absent. Modern variance X boost gradient boosted okay. Wm is derived from the exponential loss. Okay, let's see where.
Trying to approximate that, once you see a data instance of a certain form, what is the label that you should predict? So this type of learning is discriminative and supervised. And this is exactly where methods like deep learning excel.
Right.
And what you do is you define a loss function
Right.
in the parameters that you're trying to optimize for the particular machine learning model.
Right.
And it's also a function of the actual sample that you're given.
Right.
And when you look at these parameters, these theta parameters,
Right.
they sit in some high dimensional space themselves.
Right.
And each one of the entries of these theta vector is actually a 32 or a 64-bit precision floating point number. That's how it is represented on a computer, a digital
Right.
computer. And when we talk about things like deep learning, then this parameter space is extremely high dimensional. We are
Right.
talking about millions of weights.
Right.
So you use at least 32 bits per weight, and you have millions of them, whereas the largest quantum computer we have has 2,000 qubits. So there seems to be a misfit between this continuous type of optimization and what we can do on a quantum computer. So we have to think a little bit differently. There is hope. You can use quantum computers for optimization, but not for this kind of problems. So let's take a look at ensembles. So in ensembles, for instance, you can take a couple of large neural networks, and what you want to do is you want to combine them into a single strong predictor. So for instance, each of these neural networks gets a couple of instances wrong, and there would be other neural networks who would compensate for that mistake. And how you combine them is a big open question. So you want to weight each and every one of the neural networks so their overall prediction is actually stronger. And when you look at this starts to get a discrete flavor, because now you have discrete many neural networks, and while this combination of weights is real valued or continuous valued, what actually matters is the relative importance of each of these neural networks, so there's a way to discretize it better. So this idea of ensembles have been around for at least 20 years, slightly more, and they're still very important. Like many of the Kaggle competitions are won by ensembles of neural networks. And one of the first algorithms that made this idea extremely useful was AdaBoost. So what it does, it keeps expanding this ensemble sequentially. So it adds a new learning model to the ensemble one by one. So if you have less than the available models, then what you do is you take the previous ensemble that you did, that you ensembled so far, and you add the new model with some corresponding weight. And the way you calculate the weight of this new model is by looking at the exponential loss. You factorize this exponential loss into two parts, the loss coming from the previous ensemble and the loss coming from the new addition. And if it's a good model, then it will have a higher weight. And if it's a not so good model, it will receive a lower weight.
Right.
Regularization is absent, which means that it will use up all of your k available models. So even if something is very bad, it will still be in the ensemble. And if it's a predictor that's strongly correlated with one of the other predictors, it's still going to be there, even though it doesn't really contribute anything new.
Okay.
Nevertheless, there's all sorts of modern variants which address, for instance, this problem. One is called XGBoost, and another is called gradient boosted trees. These are very important algorithms. Even in today's machine learning, these are actively used. And it's worth looking at boosting methods and ensemble learning and see how quantum computers can help.
Nice, nice, nice. He's really
Planet
good.
Fitness.
He's really good. I mean, these are complex issues that he makes appear very easy. And going between the foundations of quantum computing and giving an overview of machine learning in a way so that you feel like you've got a good grasp on what's going on, and then sort of trying to bring them together. I feel very calm and confident that it's all going to come together really nicely. So really well
Let's
done.
continue our exploration of ensemble methods. But this time around, let's take a look at what we can do with a quantum computer. So when we talked about AdaBoost, we mentioned that we used an exponential loss, and there was no regularization term. So let's take a look at how we can come up with a different objective function that would map better to a quantum computer and that would give some kind of an advantage over the classical method. So we are given a sample of data points, and data points, the points themselves lie in some high-dimensional space, and they come with binary labels in this case. And then we are also given a couple of models which were already learned. So you can think about it, for instance, as large neural networks. And we have capital K of them. So now what we do is we measure the square loss between the prediction of the ensemble, which combines the individual models, and the actual label, yi. So this contrasts with the exponential loss that we talked about in AdaBoost. So that's the actual loss part. And we have a second part here, which does a regularization. So this we take the zero norm of the W weight vector. So the zero norm is just measures how many elements are non-zero. So what it does is if we increase the value of this hyperparameter, then it becomes extremely important to have most of the W entries 0. On the other hand, if you decrease lambda, then there's a lower penalty for including more and more elements in this ensemble. So 0 means that the model is not included, and the non-zero value means that a particular model will be part of the ensemble. So this way, we can find a trade-off between having a simple model and having some addition to the ensemble that may or may not improve our overall prediction. So in principle, these W weights are not discrete, so we still talk about real values. But what really matters is the relative importance and whether they are included. So we can reduce the bit width. So we can use, just say, 3 bits to represent a weight. And now we have a discrete problem. Now we have to transform it a little bit and use our Hamiltonian encoding, namely one of the two kinds of Hamiltonian encodings, the Ising encoding, and then we can solve it with a quantum annealer or by using QAOA. So here I'm just rewriting this expression in a different way. So what I do is I expand this square loss. So now I have this quadratic term over the sum of the ensemble. Then I have this term, which measures the correlation between the output of a predictor and the actual label.
Right.
We have this term, which is just the label squared. We can get rid of it because there's no parameter in it, so it's not going to affect our minimization. And finally, we retain the regularization term as it was. So we can continue working on this equation. And we can rearrange certain terms and move the sums around. So if I write it this way, the first term, then what I get is I end up with this term which measures the correlation between the individual models. And here you have the corresponding weights between the different models. Then it should be WL here. So it's a multiplication of two weight vectors, sorry, two entries in the weight vector. Then you have this term where you measure the same thing as before. So this is the same kind of correlation between the label and the actual model, weighted by the actual weight in the weight vector, plus this regularization term. So in the regularization term, you can get rid of this square root 0. It doesn't make any difference. So now if you look at this part, what you see here is that you have elements of the W vector weighted by some numbers. So this is the bias term in the Hamiltonian encoding in the Ising model. So this would correspond to the external magnetic field in the Ising model. While the only difference is that the WK entries are described as bit strings, whereas here we have spins which take values +1, -1, but that's just a shift. That's very easy to transfer.
Right, so you got this thing, and then you got this thing. And he says this is equivalent to sigma So if you're trying to minimize your loss function, is the equivalent of minimizing the energy of your Ising model. Okay. So that calculation, instead of doing it classically to do the min of the ensemble, this is ensembles, you would throw it into an Ising model quantum computer, minimize the energy, and if you go to large ensembles, this will be quicker. So essentially using a quantum computer to improve the efficiencies which you add ensembles, which is useful for training, not for inference. Okay.
Form. And then this term here has this interaction, this quadratic interaction between these discrete variables. So this maps to the sigma I, sigma j interaction with certain couplings. So here you have your Ising model. That's all you have to do.
Very
and now
cool.
you can solve this ensemble problem on a quantum computer.
Very cool. That was very cool. I like this guy. I like this guy, man. I like this. This is very cool. Yeah, this is how you learn. This is great.
We looked at one particular problem that you can solve by mapping it to.
But again, it's not. He's saying it's for ensembles of. It's for an ensemble of machine learning algorithms. It's not for optimizing a single machine learning algorithm. Well, let's see. Let's see. This is so, and that's just using the Ising model. Oh, this is really, really cool. But at the same time, that Ising model. If I go back to it, so that's something I have to look up. If that Ising model was a single transverse field summed at the end, or two transverse fields interacting with each other. I think it was just a single one. So essentially saying it can be solved with their quantum annealer.
To an Ising model. This was a supervised problem, and it's very difficult to be competitive with supervised models on classical computers, because that's exactly where deep learning excels at. And a selling point would be for quantum machine learning is that you can solve problems which remain hard in
One
machine
second.
learning. So one of the
Let me hear that again.
we looked at one particular problem that you can solve by mapping it to an Ising model.
Right?
This was a supervised problem, and it's very
Supervised.
difficult to be competitive with supervised
right.
models on classical computers, because that's exactly where deep learning excels at.
Right, okay, so he's saying like, okay, so he's being very honest about it. So it's an academic advantage which, even if it was available today, wouldn't help that much because you prefer to do deep learning.
And a selling point would be for quantum machine learning is that you can solve problems which remain hard in machine learning. So one of these is unsupervised learning.
Right?
So deep learning and many other machine learning approaches have been making advances, but it remains a difficult problem.
Mm-hmm.
So what happens here is that we are given a couple of points in some high dimensional space, but we do not get any prior information about whether they belong to a certain class or how they cluster in this structure. So for instance, we have to figure out what the labels would be and how we would assign those labels. This is a discriminative unsupervised learning problem. And we can also ask the question, what's the distribution of these points? Can we generate new points on this high dimensional manifold? That would be a generative problem. So let's look at clustering in this lecture. So in clustering, you have these high dimensional points,
Right.
and you want to identify these clumps of points that somehow belong together.
Mm-hmm.
So if there's a nice separation, and a very simple learning algorithm called k-means can identify these clusters. So in k-means, you identify some center point of these locations, and then you assign clusters based on the proximity to this central point. This idea breaks down where the density matters. So for instance, in this case, k-means clustering would assign these points to the green cluster,
Right.
which is not correct. So what you could do instead, you can follow the density and assign points to the same cluster if they're connected in some topological way. And same thing for these green dots. So that's density-based clustering. So there are a couple of ways of doing it, and there's no clear winner. So here's one way of doing it by a quantum computer. We can think about calculating the Gram matrix, the distance between every single point in the sample that we are given.
Mm-hmm.
So we fill this Gram matrix with the distances between individual points. This is a symmetric matrix because the distance function is symmetric.
Mm-hmm.
Now, if you have the Gram matrix, that actually defines a weighted graph. So the points of the graph, a graph will be the data instances, so we can label them by the data instances, and the edges connecting them will be weighted by the corresponding distance between the points. And now we can ask, okay, so what's the highest value of a cut going through this graph? So we want to separate this graph in two in a way that the value of this cut is maximal. So that would
Right.
identify these two maximally separate clusters that we are actually looking for, looking the overall global topology of the graph, as opposed to some local heuristic.
Right.
So we can do that. So say this part of the graph is called V.
I've seen this before. Where have I seen this before? Oh, that's interesting. I guess it'll come to me.
V1, so everything on this side of the cut is V1,
Mm-hmm.
and this is V2.
Right.
Then the value of the cut is defined by the distances that cross the cut. So this will be a distance between all the points that lie on the two sides of the cut. So I'm going to call this as a Wij value. So we can expand the same thing in the following form. So imagine that you have values on the same side of the graph. So if, now let's define a sigma I value as -1 if the corresponding xi point is in V1, so in this side of the partition. And it's going to be +1 if the point is in V2.
Right.
So if you have something on the same side and you calculate the product of this, as I did here, that's going to give you a +1.
Right.
So that's going to cancel out in this equation. So it's actually not going to matter at all. So that looks good. So there's the
Oh. Where have I seen this before? I've seen this before. Oh, it's very distracting.
the point is in V2. I value as -1 if the corresponding xi point is in V1, so in this side of the partition.
Right.
And it's going to be +1 if the point is in V2. So if you have something on the same side and you calculate the product of this, as I did here, that's going to give you a +1. So that's going to cancel out in this equation. So it's actually not going to matter at all. So that looks good. So these two look equal in that sense. And if they belong to two separate sides, then they will have a negative value. So they will add, and it's a symmetric matrix. So overall, you have to normalize with 4. So this gives you the cost of the cut, and this is what you want to maximize. And now when you look at it, this is exactly an Ising model. Because here you have your spin variables taking plus from minus from values. Here you have the coupling strength, and you have some constant offset. And that's it. Now you can use quantum annealing or QAOA or any other quantum optimization subroutine that you have available and solve this problem.
Nice. That was
Something
nice.
extraordinary is on.
That was nice. Yeah, yeah. It's still bothering me. I've seen that before, and just my brain is going in overdrive trying to figure out where I've seen it. More than likely, I read it in some publication, I'm thinking.
Let's talk about kernel methods that used to be extremely popular between, say, the mid-1990s until maybe 7-6 years ago. What kernel methods do is a kind of a non-linear embedding, but they do it in a clever way. So when we talk about a nonlinear embedding, what we want to achieve is that given some data set in some high-dimensional space, which has some intrinsic topology, while this data set could be very difficult to classify into two groups by some simple function. For instance, you can have the
Nonlinear embeddings. Oh, okay.
this structure when one class is embedded inside the other. And what we do is we develop some kind of a nonlinear embedding that would pull the points apart in some higher dimensional space. So in this new embedding space, you can easily separate the two classes by, say, a hyperplane, which is...
Hold on a second, let me just go back to unsupervised learning. He talks about splitting this off, calculate the gamma matrix. I got the rest of that. That's an Ising model. A weighted graph. Okay, so one way to do it is this way. So essentially, you can use the Ising model in order to, for unsupervised learning, to speed up the cost function. Okay. Okay, so you can use quantum Ising model. So you can use quantum computers to optimize the Ising model where the numbers are very large, and so you can train it. You can train Right. So it's all for training. That's great. Yeah.
Let's talk about kernel methods.
Okay.
That used to be extremely popular between, say, the mid-1990s until maybe 6 years ago.
Okay.
What kernel methods do is a kind of a non-linear embedding, but they do it in a clever way.
Mm-hmm.
So when we talk about a nonlinear embedding, what we want to
Right.
achieve that is that given some data set in some high-dimensional space, which has
Right.
some intrinsic topology, while this data set could be very difficult to classify into two groups by
Right.
some simple function. For instance, you can have this structure when one class is embedded inside the other.
Mm.
And what we do is we develop some kind of a nonlinear embedding that would pull the points apart in some higher dimensional space. So in this new embedding space, you can easily separate the two classes by, say, a hyperplane, which is the easiest form of classifying two data sets.
Okay.
And this hyperplane would tell you that whether you're on top of it, then you belong to one class, and if you are below it, then you're in the other class.
Right.
And what kernel functions allow you to do is to do something which is essentially achieves this effect, but without having to calculate the actual embedding.
Mm-hmm.
So when we talked about clustering, we talked about the Gram matrix. So in this context, this is also going to be called the kernel matrix, which
Okay.
characterizes distances or similarities between points in the high-dimensional space, for instance, by the inner product between the vectors.
Mm-hmm.
So this would be the inner product in the original space.
Right.
And after embedding, you can calculate the inner product between these embedded vectors. And now you can define that this inner product in the embedded space is actually just some function, some kernel function. And it
Right.
turns out that if this function fulfills certain basic requirements, namely it's a positive semi-definite kernel, then you don't actually have to know
Positive semi-definite kernel.
the phi embedding. It's enough to calculate this product, which is very cheap in many cases, and you can construct very interesting algorithms. So examples include kernelized k-means. So in this case, you have the k-means clustering that we discussed, but instead of the Euclidean distance, you can come up with new distance functions. For instance, you can create this exponential decay over the Euclidean distance. So here inside you have the Euclidean distance, but now it's inside an exponential that decays fast. So remote points would matter a lot less than things closer to the centroid of the k-means.
Mm-hmm.
And another great example is support vector machines, which ensure certain sparsity structure in the model, and they generalize well. So these models went out of fashion because in essence, they are shallow, so you only calculate this nonlinear embedding, and that's it. So they are not very good in this automatic feature extraction that deep learning enables you to do. Nevertheless, they are interesting, and as you will see, there are interesting kernels that you can calculate naturally with quantum computers.
Okay, so now they're scraping the bottom of the barrel. So some algorithms that are, I guess, deprecated in machine learning can be improved upon using quantum computing. Okay.
For anyone struggling with ear ringing,
it's still worth doing and learning about and following through because interesting thing about science and math is a lot of deprecated stuff can sometimes cycle back into relevance.
So normally we would take a look at some learning algorithm, dissect it and analyze the parts of it to see whether we can find a quantum algorithm that could accelerate that part of the learning protocol. But we can start thinking about learning problems the other way around. We can start from the hardware, looking at the particular quantum computer
Right.
and what are the kind of things it can naturally do.
Right.
So we are in this era where when the quantum computers are imperfect, so we have to factor in these imperfections. And if we look at the actual capabilities, we can develop completely new learning algorithms.
Right.
So one of the first examples of this kind of thinking was a particular type of kernel for learning that can be executed on a shallow circuit gate model quantum computer.
Mm-hmm.
So in this case, we start with a very simple state preparation. And then the only thing we are going to do on this circuit is a Hadamard operation, which will allow us to do interference.
Right.
So in the first two learning protocols that we looked at, we talked about how you can map a problem to an Ising model. In other words, we used a kind of a Hamiltonian encoding. In this case, we are going to use the amplitude encoding. So if we are given some vector in our data set, which we normalize to 1, then we can encode it in the probability amplitudes in a superposition. And so then we have to be careful of how we actually prepare it. But for some data sets, this can be approximated well with shallow circuits.
Mm-hmm.
So given this encoding, we can start thinking about new kernels. So the kernel that we are going to calculate is exactly this one. It does not really have a classical analog. It's easy to calculate classically as well, but it's very natural to do on a gate model quantum computer. The shape of the kernel function is going to be something like this. So it's not like the exponential decay of the kernel that you saw in the previous video. It's slightly different, and it might be useful for certain kind of data sets.
Mm-hmm.
So the circuit that we are going to need, assuming that our data set is only two-dimensional, is the following. We will have a data qubit. Every single data point is actually going to be encoded in this single qubit. So this superposition is going to be interesting. Then we have an ancilla qubit,
Mm-hmm.
which will be entangled with the test instance that we are trying to calculate the kernel on, and the data instances that we are given in the training set.
Okay.
Then we will have an index qubit, which just keeps track of this index here. And then we have a class qubit, which will contain the label corresponding to a particular data instance. And the protocol is very, very simple. First, you have to prepare a state. The state looks a bit strange. So this is our amplitude encoded test instance, the one for which we want to calculate the kernel. And here we have our amplitude encoding data instances. Here's our index register. For bookkeeping, it's also here. Note that these are tensor product states. So these things are not really entangled here. And then we have the ancilla qubit. So the zero state of the ancilla qubit is entangled with the test instance. And the excited state, the one state of the ancilla, is entangled with our data instances. And then to finish it off, we also have the class qubit corresponding to the data instances. So we can think of it as a big black box that does all this preparation, plus we have some normalization constant to take care that this superposition is actually a quantum state.
Mm-hmm.
And what we are doing next is nothing but this Hadamard operation here. So since the zero state of the ancilla is entangled with the test state, and the excited state is entangled with the data instances, by applying the Hadamard gate again on the ancilla, you interfere the data instances with your test instance. So the state that you are going to get will have this form. You will have the test instance plus the data instance, and the test instance minus the data instance is encoded in these vectors. So that's the interference part. And now what we do is we do a measurement on the ancilla if we have a certain probability of success. So by success, I mean that the superposition collapses to this particular part. And based on this, if we get the output 1, then we just discard the result and run the circuit again. And if we get this result, so we collapse it to this particular outcome, then we do a measurement on the class qubit as well. And the probability of getting certain results here will create you exactly this kernel. So The point is that you repeatedly
Wow, okay. So essentially you do like 1,000 shots in order to get one of these, and then your hope is that the 1,000 shots is quicker than the a classical computer.
run this algorithm. Sometimes you succeed here, then you measure here, and based on that, you can calculate this kernel,
Right.
which could be interesting for a number of applications.
Right, yeah, okay. Yeah, so again, it just yeah.
Deep learning
Mm-hmm.
excels at supervised learning, and it has also been making rapid advances in other paradigms of machine learning, but there are tasks that remain intrinsically difficult to tackle by this paradigm.
Okay, I'm gonna take another break. This has been very interesting. They've done a really great job, so yeah, I'm actually looking forward to the next few lectures. I think there's another 10, 20 lectures out there. Interesting.